Hello everyone, we are approaching end of this week already. We have explored about pump and mixing systems for 3D concrete printing. I'd like to take you to more practical area when it comes to material transport system. So by this stage, end effector might sound familiar to you. It is also called print head or sometimes called printer head. An vector is a device or tool placed between pump hose and the nozzle. It often comes with mixing heads, which is the secondary mixing station, which allowing for adjusting material behavior or activating the hydration through dosing certain types of chemical additives before extrusion. Depending on the presence of end effector, regardless of your choice of mixing systems, either the batch mixing or continuous mixing, which we discussed before, the framework or configuration of 3D concrete printing can be classified into one component or 1K system, or two components, 2K systems rooted from the coatings community. 1K system represents a simplified approach where the concrete mixture is delivered to the printing nozzle without any additional mixing or alteration during the extrusion process. Essentially, it involves a single material feed, commonly a pre-mixed concrete or mortar, directly extruded onto the printing surface. The focus remains on the primary shaping process without significant alteration or additions of the primary mixing. These systems generally omit secondary mixing steps and rely on the material's inherent properties and behavior. The simplicity of 1K systems contributes to their use in large-scale on-site printing, covering extensive areas and fabricating substantial structural elements. In contrast, 2K systems involve a more intricate process. They integrate multiple components or additives into the printing process, often utilizing separate material streams that combines at the nozzle or shortly before the extrusion. These systems might incorporate additional elements like fibers or chemical admixtures or special components that enhances the properties of the concrete mixture. The key feature distinguishing 2K from 1K systems is the inclusion of secondary processes, such as inline mixing, which allows for greater control over material characteristics and potentially improves print quality. However, 2K systems often occupy smaller footprints and are predominantly used for producing prefabricated components or specialized structures where it needs higher the building rates. Examining their application in the construction industry reveals a significant trend. Large-scale on-site printing, capable of covering extensive areas like walls, floors, or entire building elements, had predominantly relied on 1K systems at the beginning due to its simplicity. Companies such as Cobalt, Apiscore, Control Crafting, and Icon have pioneered the use of 1K systems for their on-site construction projects, demonstrating their capability to print substantial structures. On the other hand, 2K systems from a company like Sika are more commonly associated with smaller scale prefabricated elements, focusing on rapid production rates rather than large continuous prints. In recent years, 1K system is still demanding in laboratory scale, but most of 3D printing companies have moved away from 1K system, transitioning into 2K system, because 2K system has a better control of material behavior and interlayer adhesion property. The limitations of each system also becomes apparent in the ability to handle the evolving material properties necessary for sustained vertical printing rates. The dynamics of strength buildup and stiffness evolution becomes critical factors in determining the height and stability of the printed structures. While 1K systems tend to hold printing due to limitations and thixotropic strength evolution of the material. 2K systems might encounter challenges in managing multiple components interactions during the printing processes. But in summary, the choice between 1K or the 2K systems in concrete printing involves a trade-off between simplicity and control. While 1K systems offer ease of use, they may face limitations in handling the stiffness evolution of material. Conversely, 2K systems provide greater control and customization for the material, but are involving far more components and parameters. The secondary mixing station is a very crucial part for 2K systems in 3D concrete printing. Therefore, a careful design is required considering a few parameters like mixer volume sizing, mixing power, and so on. It could be too detailed if I outline the entire design process, so I'll put it in as simple as possible. Firstly, the mixer size or volume sizing. This process needs to make sure a homogeneous mixing, which depends on the resident or blending time within the mixing chamber. So the inflow and outflow flow rate and blending time will determine the volume of the mixing chamber. The longer resident time, the better homogenization of the mixture will be. But if the resident time is too long, the material will be excessively stiffened. To determine the appropriate resident time or blending time, the thixotropic parameters are from the material and the type of chemical additives they are using, especially the accelerator. The mixing operation related parameters like Reynolds number and the homogenization number needs to be identified or considered for the design. Secondly, the mixing power. Obviously, higher mixing power provides better mixing efficiency, but it comes with higher operating costs. But more importantly, the bulkier and the end effector with greater mass becomes, which is not ideal for 3D concrete printing. The power requirement vary depending on the geometry of mixing chamber, including impeller geometry, mixing speed, and the viscosity of the mixture. Generally, the mixing speed and the material's viscosity are considered as constant values. The geometry of the impeller becomes vital parameter for obtaining mixing power or torque. So it seems the secondary mixing process is demanding and favorable for many aspects in 3D concrete printing, especially in the mechanical performance improvement in printed objects. To properly integrate a secondary mixing process, it often requires modification to equipment and toolhead designs customized for specific 3D concrete printing systems or material or project. Let's take a look into the current real-world printhead applications. A crucial feature in the construction process will be the start and stop operation. Some systems like the USACE system control extrusion pressure. They actually control extrusion pressure to a passive printhead. This limits precise control during starts and stop sequences in construction. In contrast, an end effector with a rotor-stator pump inside enables to control extrusion rate and pressure, while precise start and stop capabilities are also obtained. But this increases the end effector's mass and the size, potentially complicating secondary mixing applications implementation. For these types of printheads, possible inline mixing systems might involve impellers coupled to the rotor shaft with a constrained speed limited by extrusion rate. Another option involves motor driving impellers in a separate secondary mixing chamber's volume, offering speed flexibility but adding mass and volume to the end effector. Furthermore, incorporating various functionalities directly into the printhead affects its size. Again, implementing features like cable inlay systems or finishing systems demands additional mass and volume in the printhead. The current commercial printhead designs have limited functionalities at present, but future advancements might prioritize high power density motors over high power to weight ratios, considering space limitations within the printhead. This forward-looking perspective remains an essential consideration for the evolving field of concrete 3D printing. All right, here you have it. We can wrap up today's session about this time. Today, we have explored the dynamic interplay between simplicity and control witnessed in the choice between 1K and 2K systems for optimal performance in 3D concrete printing. The critical role of end effectors, secondary mixing, and precise printhead design were also discussed, and we further dealt with the current real-world printhead applications as well. We are ending our week 3 with theme in pump theory and material mixing, and I'll see you in the next video with a new topic. All right, then I'll see you there. See you then.